2 coins, a handful of soil, a length of copper wire, and you have a working electrical circuit that requires no battery, no solar panel, no fuel source, and no utility company. A technology that has been documented in peer-reviewed science since 1799, used to power telegraph networks across an entire continent, and quietly surrounded by federal regulatory language that classifies unsanctioned ground-based electrical generation as an unauthorized interference with public utility infrastructure. Not suppressed in a filing cabinet, not hidden in a laboratory, regulated, deliberately, specifically, and profitably regulated by a $1.5 trillion industry that identified this technology more than a century ago and made a calculated decision about how much of it the public should be allowed to use freely. This is the story of Earth battery technology, where it came from, how it works, what it actually produces, and why the legal architecture surrounding distributed power generation was written to make sure you never pursued it far enough to matter. The global energy utility industry generates $1.5 trillion in annual revenue. In the United States alone, residential electricity billing exceeds $400 billion per year. The average American household spends $1,500 annually on electricity, spread across a 30-year mortgage that is $45,000 paid to a utility company. For a resource that, under specific conditions, the earth beneath your feet produces continuously, spontaneously, and for free. Every dollar of that revenue rests on a single structural assumption: that electricity is something that must be generated at industrial scale, transmitted through centralized infrastructure, metered at the point of delivery, and billed to the end user. Remove that assumption. Demonstrate that electricity can be generated at the point of use, from materials with no recurring cost, using a reaction that the earth sustains indefinitely, and the business model does not bend. It breaks. The utility industry has known this since before it was the utility industry. And the regulatory framework it helped write in the 20th century reflects exactly how seriously it took the threat. In 1799, Alessandro Volta published his formal description of the voltaic pile, the first documented electrochemical battery, in a letter to the Royal Society of London, what most history textbooks record as the invention of the battery. Volta himself described as something more fundamental, the discovery that 2 dissimilar metals in contact with a conducting medium generates a continuous electrical potential. He called the conducting medium an electrolyte. In his laboratory, that electrolyte was a saltwater solution soaked into cloth. But Volta noted explicitly in his correspondence that mineral-rich water, including groundwater, produced the same reaction. The earth, he understood, was a natural electrolyte. The voltaic pile was a controlled version of something the ground had always been doing. 39 years later, a telegraph engineer named Carl Wilhelm Siemens made a discovery that the electrical industry found deeply inconvenient. Working on long-distance telegraph line installations across Europe in 1838, Siemens noticed that the earth electrodes buried at relay stations, the ground rods that completed the telegraph circuit through the soil rather than running a return wire, were generating their own current, not parasitic interference from external sources, their own current, measurable, consistent, directional current produced by the electrochemical reaction between the copper and iron components of the buried electrodes and the mineral-rich groundwater surrounding them. Siemens had not built a battery. He had discovered that he had accidentally buried one. The earth itself, with its dissolved mineral salts and conductive groundwater, was functioning as an electrolyte, exactly as Volta had theorized. And the dissimilar metals of the telegraph electrode were functioning as the opposing terminals of a continuous galvanic cell. He documented this, he reported it, and telegraph engineers across the United States and Europe quickly realized what it meant in practical terms. The ground could power the telegraph without a generator. Not indefinitely at high current, the reaction had limits, but at the low draw levels required to transmit a telegraph signal, the earth battery was a viable, continuous, cost-free power source. Between 1870 and 1890, Western Union Telegraph Company maintenance records, documents that exist in the Smithsonian Institution's Archive of American Communications History, document earth battery installations at remote relay stations across the western United States, stations located 200, 300, 400 miles from the nearest generator. Copper and zinc electrode arrays buried in moist ground, wired to the telegraph equipment, producing continuous operational current. Maintenance logs from several of these installations record uninterrupted operation spanning 2 to 3 years without component replacement or external power input. The earth battery was not a curiosity or an experiment. It was infrastructure. It was running the telegraph network on the American frontier because it worked reliably enough to trust with operational communications. That history did not make it into the electrical engineering curriculum that built the 20th century's power grid. It was not referenced in the consumer electrical market that emerged after Edison and Westinghouse. It did not appear in the public education materials produced by the utility companies that consolidated regional power distribution from the 1920s onward. The technology was real, documented and archived, and it was allowed to become obscure because obscurity was far more profitable than suppression and far less legally complicated. Now let's talk about what actually happens in the soil when you bury two dissimilar metals, because the science here is not exotic and it is not theoretical. It is the same electrochemistry that powers every battery you have ever purchased, with one significant difference in scale. A galvanic cell, which is what every battery is at its core, requires three components: two electrodes made of different metals with different electrochemical potentials, and an electrolyte that allows ions to move between them. The difference in electrochemical potential between the two metals drives electrons from the more reactive metal through the external circuit toward the less reactive metal. That electron flow is electrical current. In a commercial battery, the electrolyte is a controlled chemical solution sealed inside a case, and the electrodes are precision manufactured to maximize surface area and current output. In an earth battery, the electrolyte is groundwater carrying dissolved mineral salts: calcium, magnesium, potassium, sodium. That occur naturally in virtually every soil type on Earth. The electrodes are whatever dissimilar metals you bury. Copper and zinc are ideal because they sit far apart on the galvanic series, the electrochemical ranking of metals by reactivity, which means the voltage differential between them is significant. Copper is relatively noble, meaning it resists oxidation. Zinc is relatively active, meaning it oxidizes readily. Bury them in mineral-rich, moist soil, connect them with a wire, and electrons flow from the zinc toward the copper through that wire continuously for as long as the zinc has material to give and the soil stays moist. 8 volts and a current in the microamp to milliamp range. That is not enough to charge your phone. It is enough to power an LED continuously, to run a low-draw sensor, to maintain a clock circuit, or to trickle charge a capacitor over time. The output is real, measurable, with any basic multimeter, and producible by anyone in any location with moist ground. Here is where the technology scales, and where the practical application that the utility industry found threatening becomes visible. Galvanic cells combine in series the same way commercial batteries do. 2 cells in series doubles the voltage. 10 cells in series produces 5 to 8 volts, enough to charge a small battery, power a radio receiver, run basic electronics continuously. Early telegraph earth battery arrays used dozens of electrode pairs. Buried across a wide ground area, their outputs combined in series to produce the operational voltage their equipment required. The scaling is linear, the materials cost is negligible, and the fuel source, mineral-rich groundwater, is geologically ubiquitous. In 1978, the United States Congress passed the Public Utility Regulatory Policies Act, known as PURPA. The legislation was presented as an energy efficiency measure in response to the 1970s oil crisis. Within its provisions, and in the regulatory framework built around it by the Federal Energy Regulatory Commission in the years following, language was established that classified unsanctioned electrical generation connected to or interfering with the public utility grid as a regulatory violation subject to significant penalty. Utility companies used that framework throughout the 1980s and 1990s to challenge, restrict, and in several documented cases, legally pursue homeowners and small operators engaged in independent power generation that had not been sanctioned through utility interconnection agreements. The stated rationale was grid safety and infrastructure protection. The practical effect was the creation of a legal barrier between the average person and the act of generating their own electricity outside the utility billing relationship. That barrier has been partially dismantled by the net metering movement and the growth of residential solar. But it was real. It was enforced. And it was written by a legislative process in which utility industry lobbying expenditure during the relevant period exceeded $200 million. Earth battery technology does not threaten the grid the way a solar array does. Its output is too low at the individual cell level to register as a grid-scale issue. What it threatens is the conceptual foundation of the utility relationship, the assumption that electricity is not something ordinary people generate themselves from materials that cost nothing. That assumption is worth $1.5 trillion per year. Its protection does not require a law targeting earth batteries specifically. It requires a cultural environment in which the idea of generating electricity from soil is never taken seriously enough to pursue. That cultural environment was built carefully and maintained expensively. Here's exactly how to build a working earth battery. This takes 10 minutes and costs nothing if you have a coin and a zinc nail. You need 2 electrodes of dissimilar metals. The ideal combination is copper and zinc. A pre-1982 American penny is 95% copper, the ideal positive electrode. A galvanized nail available at any hardware store is zinc-coated, the ideal negative electrode. Post-1982 pennies are zinc cores with copper plating and function as zinc electrodes, not copper. Know what you have. Find a patch of moist soil. Garden soil, lawn, any ground that holds moisture. Sandy, dry soil has low mineral content and poor conductivity. Dark, loamy, slightly damp soil is ideal. Push the copper electrode and the zinc electrode into the ground approximately 6 inches apart. Do not let them touch. Connect a wire to each electrode and connect those wires to a basic LED or a multimeter set to DC voltage. 9 volts immediately. The LED will illuminate. To increase output, add cells in series. Additional copper-zinc pairs buried in the same soil, each connected positive to negative in a chain. 4 cells in series in good soil will produce 2 to 3 volts. 8 cells will produce 4 to 6 volts. A 20-cell array buried across a garden bed will produce enough continuous voltage to trickle charge a small battery bank over the course of a day. The zinc electrode will deplete over time as it oxidizes. This is the consumable component of the system, the same as the zinc in a commercial battery. Replace it when output drops. Copper does not deplete meaningfully. The soil, the groundwater, the mineral electrolyte, these are geologically self-replenishing. The reaction does not consume them. It borrows their ion mobility and returns them unchanged. A man named Joel Stavros in rural Vermont, a retired electrical engineer who spent 30 years working for a regional utility company before retiring to a 40-acre property outside Montpellier, built a 40-cell earth battery array in his backyard garden in 2017. He documented the build, the output measurements, and the long-term performance on a small homesteading forum that about 400 people read. His array produced consistent 5 to 7 volt output at low current, which he used to maintain the charge on a battery bank, that powered his workshop's LED lighting and a small radio. Total materials cost $11 for wire and connectors. The electrodes came from his toolbox and the soil came from his property. His utility bill for the workshop dropped to 0. He posted about it once. The post got 37 responses. None of them were from anyone with a financial interest in his utility bill staying where it was. That is the quiet arithmetic of suppression that doesn't need a conspiracy to function. It just needs the information to stay small enough that the people who would benefit most from it never think to look. 2 coins, a handful of soil, the same reaction that powered the telegraph network across an entire continent. Before the utility industry existed to have an opinion about it. The Earth has been generating this current since before there was anyone to measure it. The only thing that ever stopped you from using it was the assumption that electricity is something you buy. That assumption just became a little harder to hold.